Our movie reviews are over. We're gonna go here. All right. So last time we took an exam. So before that, we talked about buffers, I think. Yeah. And again, remember buffers typically are common ions, which we use the Henderson-Hasselbalch, David Hasselhoff equation, whichever one you want to call it there. That's the pH is equal to the pKa plus the log of the base over the acid. Where again, the pKa value is minus the log of the Ka value. So if you have a buffer and you want the pH of it, you really do have two options like we talked about. You can, again, do an ice table like normal. Remember, though, if you choose to do sort of the ice table route, you want to make sure that you do have an initial concentration on the product side for your conjugate acid or base, whichever one it may be. Otherwise, you're not really doing a buffer problem. The rest of it is really the same. You can work it out the same way. Alternatively, you could just go into the Henderson-Hasselbalch equation and obviously solve for the pH. Now, if we do add something to a buffer like volume, remember that you do need to do an ice table, and it does need to be done in moles, as that will stay constant, as molarity will change with volume. And really the purpose of the ice table is to figure out how your components of your buffer changes as a result of either adding acid or base to it. Once you're done with that first ice table, it's pretty good practice to really kind of convert it back to molarity at that point, using the total volume, which would be the volume of your buffer plus the volume of whatever you added to it, your acid or base that you added to it. At that point, you again get the same two options. You could either do an ice table to figure out the pH at that point, or again, it's still a buffer, so you could go into the Henderson-Hasselbalch equation. Any questions on that there? Yeah. The truthful answer is it's really good practice to change it back to molarity, because there will be some calculations that you'll need molarity to get the right answer. If you are going to use the Henderson-Hasselbalch equation, the answer to your question is no, you don't. You could go into the Henderson-Hasselbalch equation with moles of each of those, and it will work out the exact same way if you went in with molarity. And that's really just because of this equation you're dividing, so really the volumes cancel out anyways in the molarity part of it. So you can go into the Henderson-Hasselbalch equation with moles, and it will come out the same. But again, I would highly recommend kind of going back to molarity, because there'll be some calculations coming up where if you really don't go into molarity or not careful with it, you will get the wrong answer. So, but you definitely can definitely go into moles in the Henderson-Hasselbalch as long as the units of this fraction here are the same, moles, molarity, molarity, you can really go in with either one. It'll come out the same. Other questions? Okay. Then let's talk about everybody's favorite thing that we did last week, titrations. There it is. Good talk. No. All right. So titrations is a technique that is used, and oftentimes when we do a titration, we have a solution of sort of known concentration, and we really have a lot of times a unknown solution that we're trying to figure something out. And a titration is using, obviously, like we did last time, a burette, and we add from the burette there to our solution. And typically we go and titrate and stop at what is known as the equivalence point. And the equivalence point in an acid-base titration is the point where the moles of the acid will equal the moles of the base. So that is the equivalence point in acid-base titration. That is the point where exactly you got equal amounts of acid and base moles that are in that solution. And that's ideally where you want to stop. That shouldn't be confused with, sometimes people refer to the end point of a titration. The end point of a titration is pretty much what it sounds like. It's where you lay up your titration and call it a day, and where you stop your titration. Now, if you're doing a good titration, ideally the end point and the equivalence point should be pretty close to each other, because you obviously want to stop in most cases to do so. Now, how do we know when to stop? Well, we know when to stop when our indicator usually will change color. And we usually use some type of acid-base indicator that actually will change color to give us a visual representation of you should stop your titration. Everybody's favorite is phenolphthalein. Yes. Almost spelled right, maybe. Who knows? Maybe that'll be a bonus question. We'll see. But phenolphthalein, which you might be used to, actually works off of a pH range, and most indicators do. So something like phenolphthalein works at a pH of like 8.3 to like 10-ish. And around 8.3 pH, believe it or not, phenolphthalein is colorless. Yeah. And phenolphthalein is actually colorless in acidic solutions. It's actually colorless in neutral solutions. It turns everybody's favorite color pink in basic solutions. So as you go from 8.3, which is colorless, heading towards 10, you get all those shades of pink that maybe you saw when you titrated in 200A. My favorite, dark fuchsia pink at the very end there. But we obviously, a lot of times when you do a titration, especially if you use phenolphthalein, they oftentimes yell at you, hey, stop when you barely see a color change, right? A barely lightest shade of pink is ideally what you want to do. And there is a reason for that and why they tell you that. And we'll talk about it in just a second. And we'll also talk about the common phrase that most people hear when people are titrating, which is, I just added one more drop and the thing went super dark pink, right? I just added a single drop. I don't understand that. There was like no color and then it went really dark pink. So we'll explain why that actually happens. That's not a bad titration right there. I don't know if I could do better, but we'll see. I usually get a lot darker than that, I would say. So we use an indicator to tell us to stop. The goal of most titrations is to stop at that equivalence point, unless we're doing something like we're doing in the lab, obviously, which is we want the entire titration curve past the equivalence point as well. So we're going to look at some different types of titrations. The first titration we're going to actually look at is a strong acid, strong base titration. So this could be something like the one you did the other day, a little hydrochloric acid, a little sodium hydroxide action happening there, a little double displacement type of move, right? So we're just gonna kind of switch partners here. And we're going to make water and a salt like our sodium chloride in this case. Again, just for orientation purposes here, up in the burette is our sodium hydroxide. Down in our beaker / flask, whatever you got going on there, our HCl. So again, we're adding our sodium hydroxide here to our HCl in this titration. What we see here is a titration curve, and hopefully yours looks something like that if you graphed it, hopefully. And we have pH on the Y, we have the volume in this case of sodium hydroxide added. And this is what a typical titration curve looks like, sometimes referred to as sort of a S curve, if you will. And what we're going to talk about is how we could calculate, for example, the pH anywhere along this curve that we may be interested in. And when we look at a titration curve, there really is sort of 4 distinct spots in the titration curve. There is kind of before we begin the titration. There is before the equivalence point. There is at the equivalence point, and then there is after the equivalence point. So these are the 4 really sort of areas of a titration curve that we're interested in. So we're going to sort of look at how we would come about calculating the pH in this type of titration for each of these. So we're going to start here with really the first spot there, which is actually before we start the titration. So in this case, before we add any sodium hydroxide, we want to know what the pH is. So in this particular case, we essentially have only in our beaker HCl, right? And since HCl is a strong acid, we really don't have HCl in our beaker. We really have H plus and Cl minus, right, floating around in our beaker. And that means if I want the pH of my original solution here, since it is a strong acid, it will 100% break apart into H plus and Cl minus. And really for pH, I could go right into my pH equation and I could calculate the pH based off of the H plus concentration. In most cases, since these strong acids are usually monoprotic, the concentration of the strong acid will also be the concentration of the H plus. So you can pretty much go right into your pH equation. And there you go. First spot done. We got our pH right about here. At this point, we're going to actually start the titration as we move into sort of the second area up there on the titration curve. Now, as I'm doing a titration, I am doing nothing but continuously adding volume, right? And as we talked about, that does affect sort of the calculations we have to do. And that means that we really need to do our calculation in moles. So this is another situation where you're adding constant volume. So the molarity is constantly changing, but we do need to add moles here when we're going to do an ice table. And you will need to do an ice table because we are going to get basically a reaction that's going to occur, obviously, between the HCl and the sodium hydroxide. So for part number 2 here, when we first add some sodium hydroxide, and we are definitely before the equivalence point, we are going to get a reaction that's going to occur. So again, we're going to get our HCl. It is going to react with our sodium hydroxide here. And it's going to make, again, our water and our sodium chloride. So again here, I'm going to do a calculation, and I am making up these numbers. So in case you're curious later on, I made up these numbers just to illustrate how we would go about the calculation. So what we want to think about is, obviously, this is what we're starting with in the beaker or flask, which is the HCl. And we are adding, in this case, right, the sodium hydroxide to it as we're doing our titration. So I'm going to say initially, I'm going to start with 4 moles of HCl. And once again, made up the number off the top of my head. Now, I am before the equivalence point. Should I have less than 4 moles, 4 moles, or more than 4 moles of sodium hydroxide at this point? I should have less than 4 moles, because what I know is when I reach the equivalence point, I should have equal moles of both of those, right? So since I'm adding the sodium hydroxide, I haven't hit equal yet, right? So I got to have less than, obviously, equal at that point. So again, I'm making up the number here. I'm going to go with a nice, easy number of 2 moles. And obviously, we have 0 going on here. Now, when we do an ice table, very much like what we do when we are doing buffers and we do it in moles, we actually do know what the change is going to be. So usually if you're doing an ice table with moles, you kind of know what the number is. You don't really use X's like we did, obviously, with buffers. We didn't use X's in those situations. It is going to be our sodium hydroxide. At this point in the titration, if you want to think about it, our sodium hydroxide is the limiting reagent and our HCl is the excess reagent. We got plenty of moles of HCl there, and we have less moles of sodium hydroxide. So the change in this case is going to be -2, -2, and +2 moles. And by the way, we always know we should always choose the smaller number, right? So always want to choose a smaller number. And again, this is situations sometimes you may come across that you may tell yourself you don't want to choose the smaller number, but definitely choose a smaller number. That means here I got 2 moles of my HCl. I got nothing of my sodium hydroxide. And I have 2 moles here of my sodium chloride in this made up titration. once again, once you do the first ice table in molarity, trust me when I tell you, our moles, it's a really good idea to convert it back to molarity. So I would probably at this point divide this by the total volume. And obviously that would be how much sodium hydroxide you added and HCl you started with to convert these guys back into molarity. And again, it's just a really good practice to do because then you'll usually be in the right units that you need and you won't hopefully get the answer wrong. Now, at this point, if you're not sure what's going on in your beaker, you could use your ice table to help you. I have some sodium chloride left over and I have some HCl left over. Is that a buffer, by the way? That is not a buffer. So again, just because you got two numbers, it doesn't make it a buffer. It doesn't make it I should use the Henderson-Hasselbalch equation either. So we want to look at these two things. And when we look at sodium chloride, that is a salt. And that is what type of salt? Is that an acidic, basic, neutral salt? That is a neutral salt. So we really don't have to worry about the sodium chloride as that is neutral, which means ultimately what we have at this point is still a strong acid left over. And because this is still a strong acid, that's going to be your H plus concentration, which means at this point you once again can go into your pH equation and actually calculate the pH at this point. So before the equivalence point, from the very first drop of sodium hydroxide until you hit the equivalence point, you do need to do one ice table that does need to be done in moles. The whole purpose of that ice table is to figure out what is your new concentration of your strong acid. And once you have that, you then could go into the pH equation because again, it is a strong acid. Any questions on that there? Okay. So that brings us to part number 3. And as we see, and as you might have saw as you were doing the titrations, as you approach the equivalence point, it kind of shoots up pretty vertically here. Yeah. So typically speaking, you oftentimes will see a jump in pH to the equivalence point, and then you will see another jump in pH past the equivalence point. And again, you might have experienced that, like you sometimes added the drop and all of a sudden it just kind of skyrocketed the pH, and then maybe add a little bit more and it just continued to skyrocket, and then it started to level off again. And when we go towards the equivalence point, we do get this vertical rise. And this is the reason people say that verbiage when they're titrating, which is, I just added one drop and my indicator went crazily pink. And that is because as I go this way, is the volume changing a lot at this point? No, because we just go straight down. It's pretty much the same volume. But is the pH changing a lot? pH is changing a lot. And when you look at your indicator, like our friend phenolphthalein, 8.3 kind of colorless to 10-ish, super pink, you do not have to add a lot of base as you get near the equivalence point to actually change the pH a lot. You could do it with one drop and you'll actually change the pH a lot. And what you'll see in your indicator is it will go from like colorless to, oh shoot, super dark pink. Then maybe you got a mean instructor that says that's too dark pink, you should retitrate. Anyone? Anybody have a teacher like that that said you had to retitrate? You did? You didn't really probably need to retitrate, by the way, just so you know. You probably were okay because your volume was really, really close to it. Now, the reason why sometimes teachers are not necessarily mean and they tell you, hey, that's too dark pink, you need to retitrate, is because they don't know if you titrated like I did when I was in school, which was I was the first one done. I opened that thing up and I shut it. I said, pink, I'm going home early today. Thank you for coming. And if you weren't really careful and you missed it by more than a drop and you just opened it up, you could also be at that really dark pink way over here, right? And that is nowhere near your equivalence point, right? And you're really, really far away. So if you're titrating, you're really careful and you miss it by a drop or two, you're probably somewhere in this area, which is still very, very close to the same equivalence point volume and not going to make a really big difference. That's why, usually you should tell people, or people should be told, that it's more important that the volume that you get for every titration is relatively close to each other, and that's usually will put you in a pretty good place. But that's the reason why you see that indicator change color with very, very little base, for example, added, because you don't need a lot of base in this case to change the pH a lot as you approach equivalence point, but it will change your indicator color a lot because the pH has changed a lot. Any questions on that there? These are mysteries that we want to answer sometimes, I suppose. So what happens though when we get to the actual equivalence point and you're happy, you're light pink, you go shove that in your teacher's face and go, is that light enough for extra credit? I know. By the way, that is the magic words that make everybody get light pink, right? Extra and credit. And all of a sudden, everybody in the classroom can titrate light pink amazingly. But let's see what happens when we do get to that equivalence point. So at step number 3, we're at the equivalence point. And again, we still are going to have our reaction here of our HCl plus our sodium hydroxide. And we get a little bit of water, a little bit of sodium chloride still. And again, I'm still going to use sort of my made up values here to illustrate what we got going on in terms of the calculations. Once again, we're starting with this guy and we're adding this guy. And initially, I'm going to start with my 4 moles of HCl. Now, when I'm at the equivalence point, how many moles of sodium hydroxide should I have? Should be 4 moles. Yeah. And that is also really important because sometimes when you're doing a titration problem, they may not tell you the volume to reach the equivalence point. So there are a few different ways that you could figure out how much volume you need to reach the equivalence point, because you may need it for a calculation. One way is pretty simply, you need to have equal moles of both of these guys, and you most likely have the molarity of your sodium hydroxide. So the moles, the molarity. You could just solve for the liters, and that will tell you the volume needed to reach the equivalence point. You could also do the equation that people use incorrectly a lot of times when they're doing titration problems, which is the dilution equation. As long as it's a 1-to-1 relationship between your acid and base, you do an M1V1 equals M2V2, where the 1s are your acid and the 2s are your base, and you can solve for V2, and that will give it. If it's not a 1-to-1, you should not use that equation because it will not come out right. So sometimes in these problems, you do need to figure out how much volume to reach the equivalence point. Sometimes they will not tell you that. So there are different ways you could kind of figure it out. Here we have 0. Good news at this point is I don't think you can pick the wrong number, hopefully. That's a 4 is the only number on the board except for 0. I guess you could pick 0. That would be wrong, I suppose. I guess I wrote the wrong number there, so let me write the right number, plus 4 on that side. We're going to go nothing, nada, and some 4 moles of this guy. Once again, we're going to convert back into molarity here after our ice table, and again, using the total volume. This is basically the definition of equivalence point. We have no acid left over and no base at this point. They have used each other up, basically. At this point, we're looking for what the pH is, and we can see from our ice table, the only thing we got left is sodium chloride. And as we just talked about a second ago, what's the pH of that? That's neutral, which that's a big pH of 7 we should expect at the equivalence point here in a titration of a strong acid and strong base. So when you did yours, you got a point somewhere in that 7-ish range. That would probably be where the equivalence point would have been. This will always be a pH of 7 in this type of titration because the acid is strong, the base is strong, which means the salt comes from both a strong acid and strong base, and neither part of it's going to go through hydrolysis in this case because they're relatively weak. Any questions on that there? Yeah. No, it's okay to use. I was actually more talking about like in 200A, like a 200A type of problems. Instead of doing like stoichiometry correctly, they'll just always use that equation. even if the relationship between the acid and base is not a one-to-one relationship. Like if you had like sulfuric acid or something like that, and they usually will get the wrong answer. So in this application, it's okay to use it. It still does need to be a one-to-one relationship, which most of the time our acid and bases will be in this case. But if it's not, you will have the wrong stoichiometry and multiple relationship. So you can just do an actual, by the way, this is really based off of the stoichiometry calculation, right? It is if you know the volume of your, I'll just do that, the volume of your HCl, and you know the molarity of your HCl, for example, those guys will cancel, giving you moles of your HCl, and then you could do your multiple relationship basically between these guys. And that's basically, you know, what that's based off of as well. So it really is a sort of stoichiometry type problem. Other questions? All right, that leaves us one last spot here. You saw the pink on your titration and you said, it's not pink enough. I want to keep dropping some more stuff in there. So you didn't stop at the equivalence point. You decided, let's just keep going. And what happens as we go past the equivalence point? So let's take a look at it. Now we're going to be at the fourth part of the titration, which is past the equivalence point in this titration. We still have a reaction happening between our hydrochloric acid and our sodium hydroxide. Still the same reaction happening there. Water and some sodium chloride. Once again, still using my same numbers here. I'm going to go with, I'm starting with this guy and adding this guy. I'm going to start with my 4 moles. But now that I am past the equivalence point, should I have less than 4 moles, 4 moles, or more than 4 moles of sodium hydroxide? Yeah, so we're past it at this point, right? So at the equivalence point, they're equal, and that didn't stop you. So you just keep dumping the burette in there, right? And all that stuff. So I'm going to make up again a number of 6, seems like more than 4. And that's going to be 0. Now in this case, my change is actually which one? It is the HCl. There's a switch that happens. The HCl is now the limiting reagent, and this is the excess reagent. And this is the point in the calculations that sometimes people don't want to believe that you shouldn't get a negative number. Yes. So again, always pick the smaller number when you're doing this. This is going to be 4 minus 4 and plus 4 moles. That's going to give me here 0. It's going to give me 2 moles of my sodium hydroxide, and we'll have my 4 moles here of my sodium chloride. Once again, using the total volume, just good practice. We'll get ourselves back to molarity by dividing, obviously here, how much acid we started with and how much sodium hydroxide we added would be our total volume. Once again, we take a lookie here. This is what we got left over at this point. Is that a buffer? No, they're not even related to each other in that sense, right? So they're definitely not a buffer. We have a salt here, which all the way through this whole process is still neutral. We don't have to worry about, which means, frankly, the only thing we have at this point is a strong base because, frankly, you're emptying your burette into the beaker basically at this point. You're just dumping in base. That means that's a strong base, which means probably that's going to give you your hydroxide concentration, which will not directly give you your pH, but will get you to the POH, and then you could get yourself to the pH at that point. Should probably be basic at that point, right? And that's where you're at the 12-ish mark there as you start to level off in terms of the pH at that point. Any questions on that there? So these are the 4 different calculations that you could do to calculate the pH anywhere along this particular titration curve. This is, just so we're clear, very specific for this type of titration where you're using a strong acid and a strong base. Any questions on that? Why don't we try one here? Why don't we try like, let's just make one up. Let's do, what is the pH after you add, go 20, I don't want to go, I'll go 23. Let's do 23 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar hydrochloric acid. All right, give it a go. I will as well. We'll take a look, see how you're doing. So again, we obviously have a titration. We're obviously adding volume. So we do have a reaction and we do need some moles. So I'm gonna start with that and get the moles here of our sodium hydroxide. Remember, you need to convert our volume into liters, divide by 1,000 or move your decimal point 3 places over, times it by the molarity here of our sodium hydroxide. Our liters are going to cancel 0.023 times 0.1, 0.0023 moles of sodium hydroxide. We'll do the same thing for our HCl here, our moles of HCl. 0.025 liters. Again, divide by 1,000 or move it over 3 places. Moles per liter. Again, our liters going to cancel here. And that'll get us here 0.0025 moles of HCl. So we're going to do a nice table here because we need to see what's happening after we add this. So our HCl plus our sodium hydroxide, giving us our water and our sodium chloride in this particular case. So initially here, we do have 0.0025 moles. For our sodium hydroxide, 0.0023 moles. And 0 of that. So this is what we're starting with, and this is what we're adding. So the question is, are we before, are we past the equivalence point? We are before because the moles of what we're adding is less than the moles of what we're starting with. So we are definitely before the equivalence point. And sometimes when you're doing these titration problems, it's good to know where you're at. Because frankly, you could kind of know what type of problem you should be doing and how the outcome should be before you get there. So the change here going to be our sodium hydroxide. Again, it is the smaller number, so minus 0.00230 minus 0.00230 and plus 0.00230. That is going to get us here minus 0.0023, 0.0002 moles. We got 0 and 0.0023 moles here. Again, I'm going to convert back into molarity. So my total volume at this point is the 25 milliliters I started with of the acid and my 23 milliliters I added of the base. That's like a 48 milliliters, if I'm not mistaken. So I'm going to divide this by 0.048 liters and convert me back into molarity. And that will get me 0.00417 molar. When I look at this table, I can see what I have left, and I have the sodium chloride and the HCl. So as we talked about before, sodium chloride is neutral, so we don't need to worry about it. So once again, it's really just the HCl here, which is our strong acid. Again, this is not a buffer. Super common. People always see 2 numbers, want to put a buffer in there, so don't do that. Here, that is a strong acid, which means that is actually our H plus concentration. So we could actually go right into our pH equation, minus the log of the H plus, and a little minus the log of 0.00417. Let's see here, that. Like a wonderful pH of 2.38 here, a little acidic pH. Question on that there. You can see how we did. We were what, 23. So that's about between those 2 numbers. So at least we didn't mess up, I suppose. Yeah. Any questions on strong acid, strong base titration? Yes. Well, you probably should, but probably seems like a right thing to do. Yeah. So in this case, yeah, you have really 3 sig figs off of the concentration, so you could go to 3 decimal places. It's okay. I'll probably be more happy with the calculation at this point. Other questions? All right. Let's talk about the next type of titration, which is on tap for tonight. Right, how bad it looks in there when we get there. We'll see. That's the same one we just did, so that's like a redo. Let's not do that one again. Uh, it's got to be here. There it is. All right, we're going to do talk about a titration of a weak acid with a strong base. So that is like the one tonight, which is acetic acid, which is our weak acid. Also pretty much the titration you did in 200A. Plus some sodium hydroxide, again, going to get us a double displacement reaction, a little sodium acetate action happening. And dare I say some water, yeah, going on. And again, the setup here is our sodium hydroxides and our burette. And again, our acetic acid is down here in our beaker. So we're adding base to our acid. We do see a very similar curve here, this sort of S-shaped curve like we saw with our strong acid. You might notice as well, though, the pH starts perhaps a little higher because it's a weak acid, right? Not a strong acid in this particular case. But this has the same 4 spots we want to talk about before we start the titration, before the equivalence point, at the equivalence point, and past the equivalence point. So we're going to go through each of these steps, so hopefully you understand what you need to do when you get there. So let's start at the beginning, which is before we do anything in terms of adding. So before we add sodium hydroxide, really at the start of the titration, you slap your pH meter in there. And once again, in this case, the only thing that is in our beaker is acetic acid, which is our weak acid, basically. So how do I get a pH of a weak acid? A nice table would be good. This is just a basic Ka type problem. So this is just a basic Ka problem. You would set up your weak acid that's going to dissociate into H plus and acetate. This, you would use the initial molarity here of your acetic acid. You have not added any sodium hydroxide, so you could do molarity, obviously. This is a normal Ka type of situation here, little X's going on. Yeah. You'll have your initial minus X, X, and X. This obviously goes into our Ka expression, where then you would solve for X. X in this case, as you can see, will equal the H plus concentration, and then you could go into your pH at that point. So a little bit more work here because we're actually starting with a weak acid rather than a strong acid like we had in the previous titration, where basically you could just go right into the pH equation. Here you do need to do an ice table. You need to do one ice table, like a normal Ka type problem. You could do it in molarity because you haven't added any volume at this point. You could make an assumption. You could do the quadratic. You could do successive approximation, whatever you like to do if you're bored. And you could solve it like a normal sort of ice table, and you could get the pH at that point. Any questions on the first part here? All right, so now after you put your pH meter in there, you decide, let's see what happens when we get to the second part of the titration. So again, this is when we start the titration, and anywhere up to the equivalence point, we are actually obviously adding volume. So now we need a ice table that needs to be done in moles. We're going to get a reaction in this case, this reaction here, right, between our acetic acid and our sodium hydroxide. So let's see what happens as a result of that. So here we go. This is before the equivalence point. And obviously, once again, we will have our reaction that we're looking at here in this one, which is acetic acid plus our sodium hydroxide. Again, it is a double displacement reaction, going to make some sodium acetate, which is our salt, and some water. Once again, in this case, this is what I'm starting with, and I am adding my sodium hydroxide. So much like we did in the previous titration curve, I'm going to make up some numbers. I'm actually going to make up the same number. I'm going to make up that we're going to start with, once again, 4 moles of my acetic acid. So much like the last one, if I am before the equivalence point, the moles of sodium hydroxide should be equal to 4, less than, or more than 4. Should be less than. So again, I'm going to go with my 2 moles as a made-up number. In this case, what has happened is our sodium hydroxide is our limiting reagent. Our excess reagent is our acetic acid. We have plenty of moles of acetic acid. The change here going to be the smaller number, which is our 2 moles in this case. That's going to get me to equilibrium here of 2 moles of this guy. 0 of that guy maybe, and 2 moles of this guy. Much like we've been talking about, always really good after this first ice table in moles, use our total volume, and we're going to convert these guys back into molarity. Any questions so far on the table? If you are not sure what's going on at this point, you could look at your ice table and see what you still have left over. That looks like sodium acetate. That looks like acetic acid. Is that anything? That is a weak acid and its conjugate base, also known as, somebody just said it, a buffer, right? So we have a weak acid and conjugate base. So different than the previous titration, when you get before the equivalence point, you actually make a buffer. And you will make this buffer. And that means that at this point, you have 2 options, as we've been talking about. You can second ice table it if you like. Or perhaps the better move would be a little Henderson-Hasselbalch action, yeah, and just go right into this guy, yeah. That probably would be the better move, but you can still do an ice table if you wanted to. If you do the ice table, again, you got to be careful that you do have somebody on the right-hand side there, for the conjugate guy there, that's not just zeros. Otherwise, you will do it wrong. So before the equivalence point, you will create a buffer. By the way, it usually will be an acidic buffer since the pH is rising, right? And it's still acidic at this point. And that requires a minimum of 1 ice table followed by the Henderson-Hasselbalch, or no Henderson-Hasselbalch and a double shot of ice tables, yeah, back to back. That is what we did here. This is the making of a buffer. And what happens as we get towards the end of the buffer? We actually break through the buffer capacity. And that's why we see a big jump to the equivalence point here. This also demonstrates that you can make a buffer out of a reaction of a weak acid with a strong base. And what the buffer is what is left over with that reaction. You no longer have any strong base left over. So you can make it in the actual beaker, a buffer by doing that reaction. But again, the buffer is not actually made up of the sodium hydroxide. It's actually made up of the result of that reaction, which is the parts at the end there. Any questions on before the equivalence point there? All right, well, then that must leave the equivalence point. And again, we see the same jump to the equivalence point. We see the same sort of jump after the equivalence point. And basically what you're doing here, as I just mentioned, is you're kind of blowing through the buffer because all you're doing is just keep adding acid, which is going to chew up the acid part of the buffer, right? And keep adding base is going to chew up all the acid part of the buffer until it jumps, because now you're just adding a lot more hydroxide at that point. When you reach the equivalence point in this type of titration, let's see what happens. So if we get to the equivalence point here, still have a reaction, which is not that. Let's do that. Our acetic acid, our sodium hydroxide, our sodium acetate, and our water here. All right, so once again, we're starting with this guy. We're adding this guy. I'm going to use my made-up number of 4. And now, of course, you're going to tell me the moles of sodium hydroxide at the equivalence point should also be 4. And we got 0 of this. Once again, you hopefully can't pick the wrong number, as 4 seems to be the only real number we got going on there. So that is going to be 4 all the way across. We get really our definition of equivalence point, which is none of that left over, none of the acid, none of the base left over. But we do got a little salt action happening here. We can convert this back into molarity using the total volume at this point. Once again, if you look at what is left over, that is a salt. How do I get the pH of a salt? Well, I got to first determine if this salt will actually do anything. And will this salt do anything? It will, right? Because it's sodium ion and acetate ion, right? The sodium is not going to do anything, right? Because it is still a neutral salt. But clearly the acetate came from this acid, which is a weak acid, which means it will act as a conjugate base, right? And it will go through hydrolysis. So at the equivalence point in this type of titration, you don't get to just put 7. You actually have to do a second ice table at this point, and that is going to be a hydrolysis ice table, where our acetate will react with the water, which is there as well. And because it's a conjugate base, the base will accept the H+, and we will hit a little bit of acetic acid, and we will form then some hydroxide. By the way, the pH at the equivalence point should be acidic, basic, or neutral. Should be basic because we are producing hydroxide. By the way, when I do this calculation, what type of K value should I use? Yeah, I need a KB. You most likely won't have a KB in this situation. You will probably have just the Ka value. So again, throwback day, we got to go back and again use our Kw here, right, to convert it back. We are going to do initially here, and this, as to some of the earlier questions, is really a good reason why you should convert things back to molarity, because when you go into this table, you do actually need a molarity probably to get the right answer, unless you're really, really careful. So again, just automatically putting things back into molarity after that first table will really set you up that you don't have to worry about kind of screwing up the calculation on the next one. So we would use our equilibrium molarity from above here. And this is going to be a normal X type table, minus X, plus X, plus X, equilibrium, molarity minus X, X, and X. And as you said a second ago, this is going to go into our KB expression. You will solve for X in this case, and we also want to remember that when we do solve for X, X is actually the hydroxide concentration. Again, not the H+ concentration in this case. So that is going to be a solve for X, which is the hydroxide. And that means that you will need to do the POH first and then to the pH in this case. So a lot different than the previous type of titration where you could just put pH 7 at the equivalence point. Here, you do need to do a double shot of ice tables. The first one does need to be done in moles, and really the whole purpose of the first ice table is to figure out the concentration of your salts. The second ice table is really just a hydrolysis type of calculation using that concentration. You should always hit a basic pH at this point in the titration because you have a weak acid, which will always produce a salt that will go through hydrolysis and produce hydroxide. So It will always be basic at the equivalence point in this type of titration. Hence why, tying it back to our favorite indicator ever, why we choose phenolphthalein, because it works at a pH of 8.3, which is basic to 10, and right around 8 point something ish is probably the equivalence point in most times. And that is why we use a indicator like that. If you use an indicator that actually changed color, like at a pH of 2, it would not do you much good in this case, right? So again, as we'll talk about, you do want an indicator to actually change its color near the equivalence point so you can visually stop your titration. Any questions on that? Yeah. It's which M? I'm sorry. Next to the eye. Second ice table. Oh, I'm sorry, down here. That's the equivalent equilibrium concentration from above. Yeah. Yep. Other questions? Okay. Go. Yeah. Yeah, so you can look at it one of two ways. That is correct. If you're not sure, you should look at your ice table and see what's left over. And what's left over is a salt in this case. And pretty much in every titration at the equivalence point, you'll be left over with a salt. And the difference is in the first one we talked about, the salt that you're left over with is a neutral salt. It won't continue to react with water and go through hydrolysis. But in this case, because the acid we started with is a weak acid, part of that salt will always go through hydrolysis and it will always act, as you said, as a base because it comes from an acid, and it will always produce hydroxide at this point in the titration. So you could either remember it that when I hit the equivalence point in this type of titration, it's just a double ice table situation that's happening. And that's the what's going on there. Or again, you could analyze the first ice table. And sometimes people overlook the information that's sort of in these ice tables, like the first one. It does sort of help you if you kind of understand what's going on, what should happen next based on what's left over. So you could always at the end of the ice table kind of look and see, what's left over. Like previously in the previous step, what was left over was a buffer, right? So if you're able to recognize that from your ice table, you should know, okay, at this point, all I have to do is figure out how to get at the pH of a buffer, which then should direct you to like Henderson-Hasselbalch. Here, when you look at the ice table, the first one at the end, what you're left is a salt. So what that should trigger is what we talked about previously, like, okay, does this salt go through hydrolysis or not? And if the answer is yes, that's where I should go next and to solve it. The good news about the titration calculations is obviously this one's a little bit more different than the first one we did, but we've actually done all these calculations. Yeah. And the hard part that people have is understanding when to do these calculations or not to do the calculations. So these are all calculations we've done previously. The hard part is to understand when you should apply it, yeah, and apply it correctly. And sometimes you just know where you are in the ice table. Like if I were doing this problem and I know I'm at the equivalence point in this type of titration, in my head, I know I should have two ice tables. I should have a salt that's going to be basic. And these are the things you want to think about. So that's why I said earlier, if you sort of understand that where you are in the titration, you actually can know what type of problem you should be doing rather than trying to figure out as you're going through it what I should be doing, right? So it's kind of like the directions thing, right? If you get the directions before you leave, right, you kind of know where you're going. If you're just driving around, go, I know where I'm going, right? You eventually might get there, right? But it's going to be maybe a longer journey and stuff like that. So understanding where you are in the titration curve and understanding at those four different points what happens makes the calculation part a lot easier. Other questions? All right, so let's talk about the last part of this journey here. And as you can see here, our pH is obviously basic there at the equivalence point. We're going to now go past the equivalence point. Again, it's not going to stop us. I'm just going to keep adding some base. So we're going to be past the equivalence point in this case. We again will have our reaction that we've been dealing with in this particular titration. That's not it. Do a little bit of water would be good. There we go. All right, so once again, we're going to kind of use our numbers here that we've been looking at. So we're going to start with our 4 moles of our acetic acid. And once again, previously, are very similar to the previous titration. If I am now past the equivalence point, we again should have more moles of what we're adding than what we started with, right? Because at this point, again, you just could think of it like you opened it up and just let it drain, right? So again, I'm going to make up the number of 6 in this case. Much like we saw in the previous step, our previous titration, there is now sort of a change that occurs. The acid actually becomes like the limiting reagent. We have less moles of it than we do of our sodium hydroxide, which is the excess reagent. Again, if you just remember, always pick the small number. You'll be in good shape. That means that really the acid here is going to get used up. And that means that when we reach equilibrium, we got none of that. We actually have 2 moles of this guy, and we have 4 moles of this guy. Just like normal, we're just going to do sort of the right thing here and convert everybody back into molarity using our total volume at this point. So once again, we can look at what we have left over based on our ice table here to try to figure out what is going on. I have some sodium acetate and I have some sodium hydroxide. Is that a buffer? That is not a buffer. And again, super common. I see 2 numbers, Henderson-Hasselbalch. I just want to use it everywhere. Don't use it everywhere because you will be wrong. We actually have 2 things happening here. We have this guy here, which is our salt and is a conjugate base and will go through hydrolysis like we just talked about in the previous step. But we also have this guy here, which is sodium hydroxide, which is what type of base? It is a strong base. Now we basically, at this point, have 2 bases left over. We got our conjugate base and we have our sodium hydroxide. Between the 2, which one is a stronger base? This sodium hydroxide is a much stronger base. So although the sodium acetate will go through hydrolysis like it does at the equivalence point, the major contributor to the pH at this point is actually going to be the sodium hydroxide because it's a much stronger base. So at this point in the titration, we actually ignore the contribution to the pH done by the salt in this case, because again, the sodium hydroxide is going to be a much stronger pH or a much stronger contributor. That means that essentially here, our strong base will give us our hydroxide concentration, which will give us our POH and then to our pH in this case. So as you go past the equivalence point in this type of titration, it requires 1 ice table to be done in moles. The purpose of that 1 ice table is to figure out the concentration of the strong base you're dumping in there. And once you have that, you can get to the POH and then to the pH. As you can see here, a much different set of calculations happening in this type of titration versus the strong acid, strong base titration. But again, it is all of the calculations that we have done up until this point. The key is to know when to do it. Yeah. And again, understanding where you are in the titration curve, understanding when you look at it, you should know the calculation really before you pick up the pen or pencil to do it, and it makes it a lot easier. So to review, looking at our titration curve here that I obviously scribbled all over, so I'm going to just erase all that there. In this type of titration, just a summary, at the very beginning, you need 1 ice table for a weak acid. It is basically a Ka problem. Before the equivalence point, you need a minimum of 1 ice table in moles, and you will hit a buffer at this point. Once you hit the buffer that you have, you can again choose either a second ice table for the buffer or the Henderson-Hasselbalch equation, which again, I would probably go with that route to be truthfully honest with you. Once you reach the equivalence point, no doubt about it, it is a 2-pack of ice tables, right? 2 ice tables needed here. First ice table is to figure out, and it should be done in moles, is to figure out the salt concentration. Then the second ice table is a hydrolysis problem, using obviously the concentration you get from the first one. And that is step number 3. Step number 4, or part number 4 of the titration curve, you need 1 ice table, also done in moles, to get the concentration of your strong base. Could be sodium hydroxide, but any strong base, basically. That's left over. You then obviously could go POH to pH. Any questions on any of that? So this is what I'm talking about, where if you know where you're at, you should know how many ice tables you should be doing. You should know what type of calculation you should be doing before you actually do the calculation. Trust me when I tell you, it makes it a lot easier than trying to figure it out as you're going through it. Yeah, so that's why it's sometimes good to take an extra moment and figure out exactly where you're at, understand what type of titration you're doing. And again, it will kind of help the calculation part of it. Any questions on that there? All right, we will lay it up.